everything is set up, and it's all set up on timers using the the different timing for the different parts of the exam that's available on my courses. So you should be able to see those starting this afternoon sometime. But you won't be able to see the actual questions, I think, till the start times. But you should be able to see that there's a Dropbox for it. So I'll set that up sometime, maybe 2 or 3 o'clock or something today. So thanks for coming, everybody. We got about, we might as well start now, even though we're a little bit early. So there's 2 ways that we can do this, and maybe we can do it both ways too. I presented this already, but I do have a couple of slides that just give a brief overview of everything that's covered on the exam. So my intent was to kind of do that and then get to your questions. But if you'd rather just do questions, we can do that too.
I wouldn't mind going over those slides.
Okay. So that makes sense. So go ahead.
I did have a quick question about the homework.
Yes.
So I saw the email that you sent out yesterday.
Yeah.
Which broke up the different problems for next week or this week and next week.
Mm-hmm.
And correct me if I'm wrong, but at the beginning of the class, you had said that different versions of the textbook have the same problems but with different numbers.
In most cases, but not 100% of the time. But that's why we post the actual snips of the questions.
Right. Okay. I was a little bit confused because those numbers that you posted in that email weren't in the
syllabus. I thought they were in the syllabus. So
they were in the syllabus. They matched the numbers that were in the syllabus, but they didn't match the numbers in the homeworks 2 through 10.
Okay. Can you send me an email? So I'll fix that and I'll push back the due date for the homework. I think that's
okay. Okay.
I just want to make sure that everybody, that I set everything up right. So it could be, I think that maybe I was using an old version of the syllabus with the question numbers from the previous version, but they changed the version like last year or something. So I'll make sure that those are right. Thank you, Dan. I appreciate that.
Okay. All right. Thanks.
Let me make a note to myself. Perfect. Any other questions before we get started? All right. So, obviously, as you know, we got the exam this afternoon or this evening. So there's a couple of things that we started off with from the sort of pre-lectures, right? So we want to know some basic principles of thermodynamics, right? There's this big thing about units, right? So units and carrying your units through your calculations. We're going to end up doing a lot of unit conversion in this class. We talked about in those initial lectures that I asked you to watch on your own time, this kind of issue with mass versus weight and how it's not as big a deal in the metric system because we have 2 different units for that. But in English or US units, we have this thing where pounds mass and pounds force have the same name, right? And 1 pound mass has a weight of 1 pound. And that gets confusing and it sort of breaks the equation we normally use for Newton's second law, which is force equals mass times acceleration. So that weight is going to be G over GC, right? So that's kind of like an acceleration times the mass, right? So that you get 1 equal to 1 instead of 1 equal to 32.2, right? And then we've got the problem solving method, right? We talked a little bit about pressure and what pressure is. And that was kind of a way to introduce this idea of unit conversions because pressure is a unit that we'll often have different units for. So, from pascals to kilopascals to bar to atmospheres to, PSI or pounds per square foot people use, right? So that was kind of an idea of getting an idea of what this intensive properties are, but also about unit conversions. We talked about work and power and heat transfer modes, just some definitions here. Then we talked about what is the first law, right? Now remember, this is only for closed systems. So the first law we'll be using will be delta E is equal to Q minus W. But in order to write that equation down, you have to tell me that the system is closed, right? And then we started to talk about how do we deal with the left-hand side of that if we have solids, liquids, or ideal gases. We learned about tables, right? For steam tables, we have to be able to use subcooled liquids or find subcooled liquids or two-phase mixtures or superheated vapors, right? So knowing your way around kind of that vapor dome, PV and TV diagrams. And then you might have to find things like specific volume if you want something for a pressure volume relationship, or the change in specific internal energy to deal with the left-hand side of the first law, right? We need to know how to deal with steam, right? So liquid water, steam, and two-phase mixtures. But we also talked about ideal gases, right? And how we can deal with ideal gases on a table using table A22 with variable specific heat, or using constant specific heat, making sure that we use CV times delta T to be equal to delta U. So week one, there's just a whole lot of definitions, right? So, you can watch those things again, or just know where to find those definitions. It's not uncommon for a multiple choice question in a thermo exam to be something like, which one of these answers best represents the definition of the word adiabatic, right? And you'd look at what the things are, and then you have to pick the right answer, right? And again, units are always going to be an issue here, right? So there's definitions that are covered in those week one slides, but those aren't necessarily the only definitions that we'll talk about. For example, you might be asked what a polytropic process is. And I don't think that's something that we talked about in that first week, but we've talked about that since. Here, we're not going to do questions about pressure. So this is a little bit of an older thing. So you don't need to know about static pressure for the exam, for any of the exams in this course, except to know that pressure is a unit and there's this problem with mass and weight, right? So again, you won't have to do this equation here. But then we start to talk about what's the first law, right? And there's some words that, describe what the first law is, but basically what it tells us is the change in energy in a system over time is equal to all the heat that comes in minus all the work that goes out. Or at least that's the version of the first law that we'll use for closed systems in thermodynamics class. There are obviously different types of energy, but in thermodynamics class, we're really interested in this energy transaction between heat and work. So those are the terms that survive in this equation, right? I have this kind of schematic of the universe here that I've talked about many times, right? That kind of tries to describe what this equation means, but in picture form, right? And first we talked about how to find the work, right? Work is the integral of PDV, right? Sometimes it's better to find what the work is by drawing out a PV diagram and finding the area, right? So not necessarily with this one because I can't find the area right there, but if this was a linear decrease from 1 to 2, instead of integrating that function, I would take the area of a rectangle and the area of a triangle, right? But if it's a more complicated function like PV to the 1.5 or PV is equal to constant, then I'll actually have to do some calculus that the work is the integral of PDV, right? So I need to know some function. I need to know pressure as a function of volume, right? So for a polytropic process, PV to the N is constant, or P is equal to some constant divided by V to the N, where V is volume here. I put that back into my equation and I do some integration. Now there are some set answers depending on what our PV relationship is. And if you just want to remember those, you can, but start with this equation, right? Because remember, on the test, your job is to try to demonstrate your understanding, right? My job is to try to look at what you've written and figure out how much of this you actually understand. So if you just wrote down the work is equal to this equation, but it was actually PV is equal to constant, so you wrote down the wrong equation, there's nothing I can do for you, right? Because you just wrote down an equation and that equation is wrong and you didn't demonstrate that you knew where that equation came from So all you did was write down a wrong equation, and there's nothing that I can do to help you, right? So try to be, explicit with your understanding. And a lot of times, to me, that means you start with the fundamental version of the equation and you work it symbolically as far as you can, and then you put numbers in. And when you put numbers in, you put units in as well. Because I know what the unit conversion mistakes that people usually make are, right? So don't be surprised if you see those kind of things on the exam, right? Because that's part of what we're trying to test for here. So after we find work, we started to talk about what's going on the left-hand side of the equation, right? That E, right, is the total energy at a particular moment in time in our system, right? So it's the sum of all the different energies, right? Kinetic energy, potential energy. We talked about spring energies and internal energies, right? But these are all extensive properties. So we could divide all of these things by mass to get the intensive version of these properties. We'll make some assumptions in this class often, right, to eliminate kinetic, potential, and spring energies, because really most of the problems we're interested in, it's the change in the specific internal energy or the change in the internal energy that drives this difference in the heat transfer in the work, right? Because oftentimes we're interested in boiling water, and the internal energy difference is very big between liquid water and steam, right? So this is pretty important for us, right? So your first law, after you've made some assumptions, might look like this. You'll find that the work is the integral of PdV, and then you'll get that delta big U is equal to mass times the change in the specific internal energy. Remember, the change is always the state at the end minus the state at the beginning, right? And then you can use that information to find the heat transfer associated with the process, right? Now, how do you find delta U? This is kind of like, this class is a bit like a choose your own adventure book, right? Or maybe like something, I don't know if people probably don't still play something like Temple Run. I used to, when I lived in Toronto, I'd take the commuter train in. So I was on the train like 2 hours a day. So I played a lot of Temple Run, right? And Temple Run's, you're always making these decisions, right? You're going left and then you're going right, you're jumping. And that's kind of what this is too, right? We've got this change in the internal energy, right? But which direction do I go, right? I got to ask myself, what's the fluid, right? Is it water, right? If it's water, then I got to ask myself, is it a liquid? Is it a two-phase mixture? Or is it a superheated vapor, right? And if it's an ideal gas, I got to ask myself, is it constant specific heat or is it variable specific heat, right? And then I use different strategies depending on the answer to find what the internal energy is or the change in internal energy, right? So we got introduced to this idea of a TV or a PV diagram, right? And we know that if it's water, it's got this vapor dome on it, right? There is no vapor dome, or at least the vapor dome is very, very small on the diagram if it's an ideal gas, right? But if it's water, we're close to the vapor dome because we're trying to boil things, right? Or condense things, right? So we have this subcooled liquid region, which is above the vapor dome and to the left. Superheated vapor is above the vapor dome and to the right of this critical point. Remember, the critical point is here, the highest temperature and pressure at which you can get a two-phase mixture at equilibrium, right? And then under the vapor dome, you have some combination of saturated liquid water and saturated vapor, right? Saturated steam. Right, but then for ideal gases, right, we started to say, well, these things are pretty important too. Things for like automobiles and jet turbines, right, or jet engines. They're going to use gas or something like it, right? So we need to figure out how do we figure out the change in specific internal energy for gases, right? And then we talked about this idea of the compressibility factor, right? That's what Z is, right? And if the compressibility factor is 1, we get an ideal gas, and we get compressibility factors equal to 1 when the temperature of the gas is much higher than the critical temperature, right? The temperature at the top of whatever vapor dome exists for that gas, or if the pressure is much higher than the critical pressure, right? Or sorry, much lower, right? Because as pressure is on the x-axis, as it gets very low, then this goes down to 1, right? And as the temperature gets very high, then this becomes very flat up at 1. And if Z is equal to 1, then we have PV is equal to, we might say in science class, nRT, but in thermodynamics class, because we're not talking about moles, we're talking about mass, right? So kilograms or pounds, right? So we'll say PV is equal to M, the mass, times R, which is the specific gas constant, times T, right? We have to remember that the specific gas constant changes for every gas. And to find the specific gas constant, we take the ideal gas constant, which is the same for every gas, and we divide by the molar mass. I believe that you can find molar masses for specific gases. It's either on table A1 or maybe table A20, but you might want to just flip around those different tables to get an idea for where you can find different things. Now, the ideal gas law is kind of a nice equation because we can use it in different ways. If I know the pressure, the volume, the mass, and the gas, so I can find the specific gas constant, then I can find the temperature, right? But maybe I know the pressure and the specific volume, right, and the gas, and then I can find the temperature, right? Or if I'm moving between two states, because we're talking about closed systems where the mass and the gas are the same, so the gas doesn't undergo some kind of chemical reaction, right, so that it's changing and its R value changes, then we know that pressure times specific volume divided by temperature is equal to the pressure at state 2 times the specific volume divided by the temperature at state 2, right? So PV over T is constant, or pressure times volume, big V over T, is also constant for ideal gases. So we can use the ideal gas law in that way, especially when we're moving between states. I like to use this version of the ideal gas law because I find that I can construct something where I'm less worried about unit conversions than if I'm using sort of the base level version of the ideal gas law. So then we talked about, for liquids and for ideal gases, we can use specific heats, right? Now, for liquids, we can pretty much always do this, where CV is equal to the partial of U over the partial of T at constant volume, and CP is equal to the partial of H over the partial of T at constant pressure. But for liquids, CP and CV are the same, so it doesn't really matter, right? But if it's an ideal gas, I got to be really careful to use CV and not CP if I'm trying to find the change in the specific internal energy, right? Because for gases, these things are different. So some kind of things that you sometimes see on tests is maybe it'll be an ideal gas problem, and I'll ask you to use constant specific heat. Maybe I'll give you R bar, and you'll have to look up the molar mass to find R. Maybe I'll give you R bar and R, and you get to demonstrate that you understand which of those two things you're supposed to use. I might give you CV and CP, and maybe K, and then you can demonstrate that you understand which specific heat do you use to find delta U, right? So those are kind of things we can do. Or I could just ask you to treat the problem as a variable specific heat problem, and then you can use table A22 to look up properties and do some linear interpolation, right? So typically here we would know the temperature, or we'd find the temperature maybe from the ideal gas law, and then we could interpolate on table A22 to find the specific internal energy. So the way I'm going to try to teach this course, right, the way hopefully I have been trying to teach this course, is that there's a process to these kind of questions, right? That there's something you can do even if you have no idea what to do, right? So if you're given some information, I would say make a state table, right? Draw PV and TV diagrams, right? Because these two things, they help you, right? If you draw a PV diagram, that might help you find the word, right? A TV diagram might help you find what the phase of the fluid is, right? Is it going to be a subcooled liquid or a two-phase mixture or a superheated vapor, right? If you make a state table, right? Oftentimes in problems, but not always, I'll even print out a state table for you. Maybe I'll put some given information in there, maybe not, right? But you can start to put that information in, and then any row on that state table where you see two independent intensive properties, then you know you can fix the state. I don't usually do this, right? But you could, especially if you had lots of processes strung together, you could make another table that that's a process table that tells you what's the start state, what's the end state, and what's the heat and what's the work. So that's another place where you can just have some accounting going on, telling you what's going on in the process. Now, I look for, if I'm not sure where to start, right, I can look for what row on my table has 2 or more independent intensive properties, right? And then I can say, okay, that's a state that I can fix. I can find U. Now I'm good to go for that state, right? Then you put that information in and you look for maybe process info, particularly if you only have one piece of information about the state, right? So if you're trying to find the pressure or the volume, and you know that PV to the 1.5 is constant, and you know that at one state but not the other, maybe you can find P at state 2 because you know V at state 2 and P and V at state 1, right? Or if it's an ideal gas, right, you can use the fact that you have the ideal gas law, that PV is equal to mRT. And that might help you find, say, a temperature at state 2. And then when you know that temperature, you can put that into CV times delta T, or you can take that temperature to table A22 and figure out what the specific internal energy is. Now you can use the first law. This is kind of assuming that you're going to find all the state information first. You can also just jump right down to here and use the first law from the beginning and get a symbolic solution. If you get a problem and you have no idea what to do, write down the first law, right? Write down that you know that to find work, you have to take the integral of PDV, right? Write down that you know you're going to assume that the kinetic energy and the potential energy are equal to 0, so that delta E becomes delta U, right? And delta U becomes M times delta little u, right? And then, just going down the path, maybe then you start to see, oh, now I can fix the state because I got my state table up here, right? I can fix state 2 because I know all that information, right? And then maybe you'll say, oh, look, the only thing I need left is one piece of information about state 1, but I know that pressure times volume to the 1.5 is constant, right? So maybe then you'll be able to do that, right? Now, if you have a whole lot of states in your system, right, you want to complete this step multiple times for different states, right? So even if you get bogged down with not being able to fix the states, because sometimes that's the hard part, and that's kind of the time-consuming part too, then I would suggest do it all symbolically. Write down delta E is equal to Q minus W. I'm going to assume some things, and that becomes delta U is equal to Q minus W. Oh, I know that work is the integral of PDV. Even if I don't even know what the pressure-volume relationship is in the problem, I can write that down. And then even if I totally get lost, I'm just sitting there doing nothing because I have no idea what to do, instead of leaving it blank, just make something up. Say, oh, my pressure-volume relationship, I'm going to say that it's linear, right? Because then even though you're not demonstrating your understanding of how to do that particular problem, you've demonstrated generally that you know how to do a problem, right? And that's certainly way, way better than leaving it blank, right? Because if you leave it blank, there's nothing I can do to understand how much you know what's going on in the class, right? But even if you have no idea how to do the problem you're asked, doing something will help, right? So how do we use process info, right? We ask these questions. Is the process open or closed? This question will be very easy to answer on the first exam because the process is always closed. We've talked a little bit about open systems, but none of that is on the exam, right? And you have to ask this question first because it describes or it defines which version of the first law you're going to use, right? So because the process is closed, then you can write down delta E is equal to Q minus W, right? So the process will be closed. We get delta E is equal to Q minus W, right? We'll make some assumptions, and that becomes delta U is equal to Q minus W. Right now, we look for some information about the pressure-volume relationship, right? Maybe that's explicitly told to us, or maybe it's an ideal gas and I can figure something out, right? Then I find that the work is the integral of PDV. Now I found the work, but I need to find what the left-hand side of the equation is, so I have to fix the states, right? And for that, I need to know what's the fluid, right? If it's a subcooled liquid, then I can use the tables, right? I would suggest using the two-phase tables, right? And remember, we said for these subcooled liquids, we can assume that the property of a subcooled liquid with a temperature and a pressure is approximately equal to the same property of a saturated liquid, right? That'd be UF, for example, but at the same temperature, right? If it's a two-phase mixture, what I'd ultimately like to know is what the quality is. Now, maybe I have to find that in a roundabout way because maybe I can find the specific volume. And from the specific volume with the quality relationship, I can find the quality. And then once I know the quality, then I can find the specific internal energy. Right? I might have to do some linear interpolation on table A4 if it's a superheated vapor. And if it's an ideal gas, then I have to know, is it constant specific heat, where I use delta U is equal to CV times delta T? Or is it variable specific heat, where I still need to find the temperatures, but then I'd go to table A22 and interpolate, right? And then finally, now that I know the work and I know the change in the internal energy, I can use the first law to find the heat transfer, right? So this, this sheet right here is what you need to know, particularly for the long answer problems. I think you can certainly expect that the long answer problems will be these kind of problems. These first law problems, maybe in one process, maybe in two processes. But this is the kind of thing you'll have to demonstrate that you understand on the long answer part of the test. So that concludes the sort of review presentation that I have. But I am happy to answer any kind of questions that you might have, or at least try to answer them.
Just a general question about the test. Will there be a place to submit our work for the multiple choice?
The multiple choice will be submitted like the quizzes. So you won't write out your answer for the multiple choice. You'll interface with it in the same way that you do with a quiz. So you'll go to the quizzes tab, and there'll be something that you can see called exam 1. And then you'll click on that and you'll go through and pick your answers.
Okay.
Any other questions?
Could we maybe just go through an example where we're using delta U is equal to CV delta T with an incompressible liquid?
Sure. So let's say you have a pipe, right? Now this pipe is going to take in water. Oh, no, no, it's got to be, I lied, right? So let's say, I was thinking about open systems. So let's say you have a sealed rigid container, right? And this container is full of water, right? Maybe you can think about this as your hot water tank, right? So my daughter, she just finished taking a shower. She takes long showers. This tank was depleted of all the hot water. Then it filled it up, right? So this is now at state 1. This is filled with liquid water at 4 degrees Celsius, right? This is at state 1. But between state 1 and state 2, right, the heater kicks on in my water heater, right? So the natural gas goes on, it's burning stuff, right? And that's heating up the water. And then at state 2, right, once my water heater comes back to where it's supposed to be, let's say, I don't know, I have no idea what these temperatures, it'll be 4 degrees coming out of the tap. I'm just going to guess here that this is something like, I don't know, let's say it's 60 degrees Celsius. How much heat went into the system? Right, so in this problem, I would say delta E is equal to Q minus W. Right, I guess first I got to assume that it's a closed system. Right? Now here I'm going to assume some other things. Right? I'm going to assume that delta KE is approximately equal to delta PE. That's approximately equal to 0. Right? So this is going to become delta big U, or if I prefer, mass times delta little u, right? And this is going to be equal to Q minus W, right? But here, there's no, this is a sealed rigid container, right? The volume's not changing. There's no piston, there's no, nothing's going on in here. So I'm going to say for this particular process, the work is equal to 0, right? The pressure is constant and the volume is constant. So it's kind of boring from a work perspective, right? So this is just going to equal Q. So if I want Q, then I need M times delta U. Right now, there's two ways that I can do this. So I can say constant specific heat, right? And then, right, this becomes mass, which is constant in the problem. Remember, these deltas are always going to be, this is E2 minus E1. It's always the energy at the end minus the energy at the beginning. So this is going to be mass times U2 minus U1 is equal to Q. This is true for both, right? So now I'm going to invoke constant specific heat. So this is become mass times the constant heat at specific volume times T2 minus T1. And that's going to be equal to Q, right? So now when I look at this, I know the mass, I know T2, and I know T1. I don't know Q. That's the thing that I'm trying to solve for. Now, what I need is the constant specific heat, right? So I probably want to look this up. I think that it's in table, I don't have the tables open. I might want to check the appendix. This could be in table 1, but I don't think so. I want to look for constant specific heats of, you know, liquids or common properties or something. I could even, because it's an open exam, I could Google constant specific heat of water. I think is it 4.2 kilojoules per kilogram? I'm not sure. But okay.
Well, I believe so.
This is a good example, right? So maybe I can't find this, right? So what else can I do, right? The other thing I could do, right? Because even for these liquids, I can use a variable specific heat approach, right? Because here I didn't find delta U, right? Instead, I didn't find the individual U's, I'm gonna find the T's. The other thing I could do here, right? I have the option of saying that mass times, this would be U of T2, so UF of T2 minus UF of T1 is equal to Q. So both of these are acceptable on the exam. This one might be a little bit more accurate, but this one, because the temperature difference here is not that big, would also be okay, right? So here, when I look at the accounting for this one, let's say I know the mass, right? I don't know, let's say this is 10 kilograms, right? Let's say I know the mass. I'm trying to find Q. Because I know the temperatures for both of these, I'm going to look these up on table A. Is it A2? Is the temperature table. So this, I want a two-phase temp on left, right? And then I just pick up the UF values for those two temperatures. So I could do it either way. If something more, let's say that I had a piston that could move here, and it moved in such a way that the pressure was always equal to 1 atmosphere. And then I increased this to some state 3, and state 3, the temperature was 120 degrees Celsius, but the pressure was still 1 atmosphere, right? Then we would draw our TV diagram, and we'd have our 1 atmosphere line. For 1 atmosphere, we know that the boiling temperature is 100 degrees. So we started here at state 1 at 4 degrees. We went here at state 2, right? This is 60 degrees, still less than 100, but we ended here at state 3, which is at 120. So I can use this, delta U is equal to CV times delta T. I can use that between state 2 and 3. Because that liquid is incompressible. It's going from liquid to liquid. I cannot use CV delta T as I go from 2 to 3, because then I start to introduce vapor into the system, and vapor is compressible. It is not incompressible. So here for state 3, I have to look this up on table A4. I would find P is equal to 1 atmosphere, right? That's going to be a table that looks like this. Temperatures, I'm looking for 120 degrees, and then U is over here, and I'd pick that off, right? So if I was going between state 3 and 4, then I'd have to, or between state 2 and state 3, I'd have to use this, right? So if I still wanted to find Q between 3 and 4, so this is Q from 1 to 2, Q from, from 2 to 3, we're going to make all the same assumptions. This is still going to be the same mass times U3 minus U2. Now I have to use that this is going to be UF of T2, and this one I'm going to get from A4. So I know that's maybe a little bit more than you asked, but we can only use CV times delta T when it goes from liquid to liquid, right? Or if it's a solid, right? If it's solid to solid, solid is also incompressible. Does that answer your question?
Yeah, thank you.
You're welcome. Anybody else? We've still got 15 minutes or so. And I'll stick around if people still have questions after.
What are the names for each of the like the PV is equal to C? Like, what are the names and like ranges for when? Like, I don't know how to really explain it. I know it's on one of the slides, but I don't know which slide it or which.
I think that, and that's okay. You don't need to know that. So there was a slide that was saying P, V, N is equal to C, and then it had some kind of brace bracket over here, and it was talking about for different values of N. So like if this one's easy, right? But if P, V to the 0 is constant, oops. Right? That's the same thing because V to the 0 is just 1, right? So that's the same as P is equal to constant, right? So if N is equal to 0, then this is isobaric. Right? So baric, like bar, like the pressure unit, that means it refers to temperature, right? So in this case, then now there are some other ones like, there was some cases where it was adiabatic, some cases where the work was much bigger than the heat transfer. You don't really need to know those. That's okay. But isobaric, that means constant temperature. Isometric means constant volume. What else do we know? Isothermal means constant temperature. Adiabatic means no heat transfer. I think that's all we need to know so far. Does that answer your question?
Yeah, thank you.
But you might want to go through there. There will be some definitions in that first couple of lectures there. And if you don't want to watch the whole videos, you can just get the PDFs are also all online. Or at least they should be. If you can't see, there should be some kind of heading there that says like Schutter's lecture notes or something like that. Those are just basically the PDFs of the lectures that I present, right? Or it might be like the 2-year-old version, so there might be some small changes. But usually it's just the dad jokes that change. It's not the content of the class. You got to keep it fresh,
What's the difference between like one of the earlier like homework questions that you gave us versus the questions that had like different stops that you were telling us about?
Okay, so the difference between so I'm not sure what you mean by the earlier questions, right? But
like
the
the
ones with the
questions
stops,
you
they
gave,
work like this, right? So this is my terrible drawing of piston inside a cylinder, right? But let's say it moves, right? It moves this way, right? So this is state 1. And over here, this is going to be state 2, but it's also going to be state 3. So from maybe there's a heat transfer coming in. We'll pretend that's a red line. Now this goes from state 1 over here to state 2, right? So now if I was making a state table, right? Maybe I'd want to have pressure, volume, temperature. Maybe instead of volume, let's do specific volume. State. And we want to know the specific internal energy, right? So now from state 1 to state 2, I can see here that the volume increases, right? So V1, V2, right? But V1 is bigger than V2, right? So here I would expect to have some kind of pressure volume relationship. Let's say it's linear. Right, so here if I drew this, oops. Right, so here this would be pressure versus volume. Now we're going to start at a small volume and go to a big volume, right? So if it's linear, who knows? Let's say it's increasing, right? So we go from a small volume up to some big volume, state 1 and state 2. But then between state 2 and state 3, because this here is on the stops, right? What I know about, so, it's trying to expand, but it can't, right? So because it's trying to expand, but it can't, right? V3 is equal to V2. Right? But because it's closed, M3 is also equal to M2, right? So that means that V3 also has to be equal to V2, right? Because this is V2 over M, and this is V3 over M. Right? So now if I wanted to draw state 3, it would be vertically up here. So because if this is a vertical line, right? So for both of these, I would use the idea that work equals area under a PV diagram, right? So there's some area of this rectangle and area of the triangle, right? So the work from 1 to 2 is going to be the rectangle plus the triangle. Got to watch my units here, right? So I want to have my pressure in, say, kilopascals and my volume in meters cubed if it's metric, right? But the work from 2 to 3, the area under this vertical line is equal to 0, right? Because the volume doesn't change. In order for there to be work, right? Because the work is the integral of PdV from let's say point A to point B, right? If the volume doesn't change, if the system is rigid, right? Or if the volume is not changing between any two states, there is no work, right? And that's because if the volume stays the same, we either have a vertical line up on a PV diagram or a vertical line down on a PV diagram. And in both cases, there's no area under that vertical line, right? So when the volume is constant, then the work is 0, right? So here I would say, so this would be, mass times, after I make some assumptions, U2 minus U1 is equal to Q1 to 2 minus W1 to 2. But also the mass of U3 minus U2 is equal to Q2 to 3 minus W2 to 3. But this W2 to 3 is 0. So we can just cancel it out. So now what I'd want to do is, if I had the mass, right, I could find the work, right, because I have this relationship, right? So that's just going to be this rectangle plus triangle. And then I want to fix all these states, right? So I have to fix U1, U2, and U3. And after I do that, then I can find the heat transfer between 1 and 2 and the heat transfer between 2 and 3. Does that kind of answer your question?
Yes, thank you.
You're welcome. And you can certainly see a problem like this. I think this is as complicated as we would go, 3 states and 2 processes. I don't think we would make you do 3 different processes, right? But you certainly could see 3. I think historically, if there were 2 problems, maybe one of them would go between 2 states with a more complicated PV relationship, and one of them would have 2 processes, so it'd have 3 states with sort of less complicated PV relationships. You guys, do you feel comfortable with all the interpolation stuff and finding the right, the right states, using the correct, what's it called? Drawing PV and TV diagrams. You feel comfortable with that? Because that's another kind of pretty new idea in the last couple of weeks. Sounds good. Go ahead.
Let's see. You just said something about, I don't know, it just came out of, I just forgot what I was about to ask.
I was asking if you felt comfortable with PV and TV diagrams and linear interpolation.
So what about if you have a subcooled liquid and the temperature doesn't fit in the range of where the tables start or finish. I remember there was a question like that in the homework.
So you have a subcooled liquid where the temperatures are...
I remember that the number started at 500.
Oh, right. So that was the first time, right? Because before then, I think I know the problem. Oh, my color scheme here is terrible. Right. So if this was temperature versus specific volume. So that was before, right? So there was one case where we knew it was a subcooled liquid, right? And then we tried to go to table A5. But table A5, the pressures on table A5, right? That's the table that you go to for subcooled liquids, are huge, right? And the reason that here the pressures on A5 are very, very large, because it's not worth their time and effort to make those tables and put them in the book and make you pay for the paper that they printed on, right? Because you don't really need to, right? So if it's a subcooled liquid, right, you have 2 choices. If it's subcooled liquid to subcooled liquid, then delta U is equal to CV times delta T. It only really works for delta U. If you just want to know a single state, which you could still do for subcooled liquid to subcooled liquid, right? Then here, that U of some pressure and temperature is approximately equal to UF of that same temperature, right? And that's true for V, H, although we probably won't see much H's, S on the test here, right? So you can approximate these all as the saturated liquid line. So basically what we're saying is that this state here, state 1, is approximately the same. If we called this 1 prime, we would say state 1 is approximately the same as 1 prime if we're looking for U, V, H, or S. So for subcooled liquids, probably I would just go to the 2-phase table and look for either the temperature or well, it's probably best if you know the temperature, but the pressure, if you know the pressure, you can do that too. And just look, because this has a huge range of data on it, right? It's going to go all the way from basically when the liquid turns to a solid, right? All the way up to here, the critical point, right? Although I guess the liquid turns to a solid at different points at different pressures. But you're going to have a real wide range of temperatures there. And I don't think I'll ask you something on the test that, that would fall out of that range. I guess if it did, or if for some reason you didn't have access to the table, if it was a subcooled liquid to a subcooled liquid, you could do this. It's a worse approximation, right? And we saw this in the example. But you could also, if this was at constant pressure, you could find this point here, which is 1 double prime. So if UF of 1 double prime was here, you could do this and then do CV delta T to come down to this where the temperature is. So you could find the temperature here. But that's less accurate. Okay, no problem, Dan. Does anybody have other questions?
At some point, you said that people usually get confused about when you say PV is equal to not constant, but PV is equal.
Sometimes when people see this, PV is equal to constant, for some reason, some people think this means linear, right? PV is equal to constant is not the same as linear. If it was linear, then it would be P is equal to MV plus C, right? But we never really talk about it like this because integrating something like that, it's not like it's hard, but it's time consuming, right? If it's linear, right, you just draw it. And then it's a rectangle plus a triangle. If it's P, this is a tricky one, right? Because now P is equal to C over V, right? And then when we integrate P dV, we're going to get the natural log, right? So it is tricky, but it's not the same thing as, and linear is also can be tricky if you're not used to doing it. It ends up being not too bad once you do this. But when you do this, I want this volume probably in either meters cubed, or maybe it's tricky, right? So if it's imperial, or if it's metric, I want it in kilopascals in meters cubed, because kilopascals times meters cubed is going to be equal to kilojoules. Now, if this is PSI and this is foot cubed, then we're going to have to, basically anytime it's an imperial problem, the units are going to be a problem, right? So here I would write this is pounds force per inches squared times cubic feet. So I wouldn't write PSI here. I'd actually write out the fraction. And that's probably a good habit to be in for pascals, right? So this would be kilonewtons per meter squared, right? So now here I see this, that I either have to, it depends if I want foot pounds or if I want inch pounds, but I'm either going to have to convert the inches into feet or the feet into inches, right? So here there's a unit mismatch here because these are both lengths, right? But one's in feet and one's in inches. So I got to do something with that. Probably for me, I would take 12 inches over 1 foot squared, and that would get rid of the inches. But alternatively, I could also take, I still want the feet on the bottom. I could do 12 inches over 1 foot cubed, right? This would give me inch pounds, and this would give me foot pounds. Right? And you can see the difference is just you multiply by 12, right, to get from an inch to a foot. So anytime the problem is in imperial, and there's 2 unit systems and there's 2 long answer problems, so you might be able to make some assumptions about the unit systems you'll see on the exam. Any other questions?
No, can't think of any.
All right. Well, thank you very much, everyone. Just to make sure everything's fair, I'm going to be essentially out of communication. I'll still be checking emails, but I won't be answering questions about the exam. The exception will be if you can't find the materials, right? So if you get there and for whatever reason you can't see the test, then email me and we'll figure something out. I'll get it available to you and we'll adjust whatever the deadlines are or whatever.
And my time and everything is set up already?
So that's all set up just like we set up in the email. So I've set it up a separate thing with specific access. So all the exams are set up so that only the people who can access the particular time limits that are associated with those things have access to them.
Okay.
Okay, so it should work like that, but if for some reason you can't see it, just shoot me an email.
Okay.
Okay? Thanks, everyone.
Yep. Have a good rest of your day.
You too. Good luck, everyone.